For me, there's a limit. But okay, so long as these examples are recorded, good lah. So how, people? It's a more fun. There are different mechanisms for each of them. The reason why half is there. Shall I let you think about this over the weekend? How? Okay, I shall I shall explain the mechanism for this one. The usual case whenever there's dissonance is always because we did not take into account certain things. Yeah, it's sometimes because we didn't take into account certain things. What is that thing we did not take into account? It starts from rest. I had implicitly assumed that it ends at rest. Is it possible for it to hit here and be at rest? You see, this M over here, there's mg over here, and it's always mg. But the force over here is always smaller than this force from here to here. Do you agree? So when it reaches here, it must be moving. Agree on? Yep. Therefore, in order for it to start at rest and end at rest, there must have been a, okay, this is bad drawing, invisible hand over there. That means I actually lower it. Now this is the first part of the thing. Now therefore, do you agree that force of hand plus force of spring must be equals to mg at all times? Therefore, force of hand must be equals to mg minus F spring, which means the force of hand must have been something that looks like this. So what's the work done up to x naught, and this is initially mg. Initially when x is 0, it must be mg because the spring is not exerting any force. So what's the work done by the hand? And is the work done by the hand positive or negative? Let's take a look. The force exerted by the hand is up. What's the displacement? Down. What's the work done, positive or negative? The angle between the force and displacement is 180. So it's negative. So what does it mean when I do a negative work? It means I reduce the energy. So what happened is that if it had dropped down over here to here, without the hand, it should be mg x naught total energy. But because of the work done by the hand, it reduces the energy by half mg x naught. That's why the energy remaining over here is only half mg x naught. 明白吗? Can? So sometimes when things don't go right, it's because they consider everything. You didn't. Can? Then the other one. This one, what did we not consider? In order for the sand to move together with the belt, there must be this very magical force that starts with F. Friction, exactly. If there's no friction, what will happen to the sand? It just stay there and then the belt just stay there, right? So because there's friction, so they agree that there will be points where the friction, the belt is actually moving against the sand. Rubbing against the sand when the sand's velocity is lower than the belt's velocity. So that rubbing action actually causes the energy to be lost. And it accounts for the half mv squared upon t over here. So we did not consider friction just now. That's why it accounted for this. Now this is even more interesting. Why is it that there is half QV loss? No matter what, some people will say that it's resistance across, not air resistance, it's resistance in the wire. Then my question is, what if I use a superconducting wire? There's nothing over here that talks about the wires. It's just half QV. It's something that belongs to the capacitor, nothing to do with the wires, and this is the QV delivered by the battery. So it's nothing to do with the resistive wires. Now the reason is because I cannot show you the detailed derivation because it requires the horror story again of integration. Yeah, but the mechanism is this. When you charge up a capacitor, you build up an electric field. You have learned in secondary school this thing called Faraday's law, right? Remember Faraday's law? Remember, a changing magnetic field, a changing magnetic flux not current, you have to be correct. A changing magnetic flux linkage induces what? Charge, current, or EMF? EMF, correct? Not current, because it may not induce current. but it confirm will induce EMF. Agree? Now EMF is as a result of electric field. Now what Maxwell, have you heard of this thing called Maxwell equation? Maxwell equations? Faraday's law is one of the 4 Maxwell equations. It's one of the 4. Now, Faraday's law says that a changing magnetic flux induces an electric field that causes your EMF. There's another equation under Maxwell equation that says that a changing electric field induces a magnetic field. Yeah, so changing magnetic field induces electric field. Changing electric field induces a magnetic field. So when you charge up the capacitor plate, you're charging up the electric field. So you're inducing a magnetic field over here. Now when the magnetic field over here is changing, it induces the electric field. And when it induces the electric field, it induces a magnetic field. So what is this chain of changing electric field and magnetic field called? Yeah, you got a changing electric field between the plates, and then it induces a magnetic field, and then it induces the electric field, induces a magnetic field. So you've got a series of inducing electric field and magnetic field, electric field and magnetic field. What do you call that? Something you learned in secondary school. It's an EM wave. So when you charge up the capacitor, what you do inevitably, you cannot not do it, is that you send out EM wave. That's why when you have radio, I don't know whether you still use it, it's no longer existing, I guess. It's all MP3, MP4 now. So in the past, there's this radio, invention called radio. If you turn on the lights, the radio actually goes bzz, bzz. Because as you turn on the lights, you're charging things in the whole circuit, and then it sends out this electromagnetic wave that interferes with the radio. Yeah. It's inevitable. There's nothing you can do with current technology. Yeah, so basically that's where the half comes in. Can? Cool. More detailed explanation can be found in the book available in popular bookstores. So you can look for it lah. Not compulsory, but